So let's do some examples to better understand the concept of vector calculus in the previous lectures. To do that, let's consider the following case. Let's suppose we are working with a subsonic compressible flow. Subsonic compressible flow velocity field. The velocity field is given as follows. Okay. Now, note that in this particular problem, let's assume that your velocity field, as you can see here, is only a function of x, is a function of y, and maybe a function of t. Okay, so and we know that. Now, from the problem itself, we can immediately see that your u is equal to 0. I'm sorry, your u is equal to 3xy minus x squared. That this term right here. Your v will be the term next to the j. That would be xy squared minus 338y. Your w in the problem is equal to 0 because I don't have a k. And what you're asked in this particular problem, you ask a couple of things. The first question you are asked for is to calculate the time rate of change of the volume. Of the volume of the fluid element at the location 4, 5, 0. Okay? Per unit volume. Okay, that's the first question. Now, if you remember from your notes, we defined that the rate change of the volume was actually given by the following equation. We showed that this was equal to 1 over the volume dt was equal to this dot v. Okay, so knowing this equal to this, and we take we do this, we can also show that this is nothing else than we did this in class, partial of x, partial of v respect to y, plus partial of w respect to z. And we know there's no z component in my problem, so it's equal to 0. Let me change the colors quick. Okay, this is only an xyz plane basically. So now I can take these quantities and I can take the derivative of these quantities as I need, right? So your partial of u respect to x will be nothing else than 3y minus 2x. That comes from this equation right here. And this will be partial of v respect to y. So that would give you 2 times x minus 38, xy minus 38. Okay, so I replace this inside here. So this will give me 3x minus 2x plus 2xy minus 38. So if this is equal to, at this location, this is 3 times 4. Remember, the first one is x, second term is y, this is z in the Cartesian coordinates. Okay, so 2 minus 2, 5, plus 2, 4 times 5 minus 38. So if you do the math here, you can show that this is equal to, this is equal to 4. And the unit of this is 4. The units will be per second. What is this really telling you? What it's telling you is that you have the rate in which your volume is growing is positive, right? It's positive, that means that your volume is actually growing. So it's saying that you have initial volume, right? And then that volume grows to this next volume and is growing at a rate that 4 per second. Okay, so another way to look at this is, we could say you have another way to look at this is, you have meters. If you want to use meters, meters squared over second over 1 meter, meter cubed per second, and is divided by 1 meter. Okay, so that's how we can get 1 over s. So what you're really saying is the velocity in which this is moving over 1 meter squared. If I was going to take just a meter squared, in 1 meter cube volume, and I move at this rate at 4 meter cube per second, that will basically equal to 4 over s. This is the strain increment of your problem. Okay. The second thing you asked in this particular problem is, what is the vorticity? What is the vorticity at that location? So we know, and we showed in class, that the vorticity confined to only one plane is actually going to give you, by this equation, you can go to the notes. We did that over k, and then taking the derivative of y respect to x gives you y squared. Okay, so this gives you y squared minus this respect to y, so it gives you 3x minus 3x k. And now if I replace my coordinates, which give me, this was at the location, so this is 5 squared minus 3 times 4 k, and that will give you 13k. Okay, this is your vorticity. Okay. If you wanted to know the rotation, on the other hand, if the problem was going to ask us in number 3, what is the rotation? What is the rotation at that point? Then what you could do, rotation we know that is 2 times omega is equal to big omega, right? This is a vorticity. So your omega is nothing else than half of this. The half of that would be 6.5 K. Okay? And so that is the vorticity. This is the rotation, and you can see rotation is per radians. You're working with angular velocity per seconds, basically. Okay, so this is how more or less, this is how we actually handle all the mathematical terms that we learn. How do we actually apply to a compressible flow is given as follows. Now, let's suppose that you asked another question, okay? The question is, for how, so the question is, can, under what conditions can this flow be modeled as incompressible? Incompressible flow. Under what conditions can we do that? If you remember our notes, I told you that the only way this can be incompressible is if we can show that this is actually equal to 0. Okay? This is the condition for flow is being incompressible. So if we go back here and now we find this equation, we show that that was actually equal to this. So I'm going to just copy paste this here. So I know that this is equal to this. The only possible way this could be 0 is if I can set this whole thing equal to 0. So if there is a combination of x, y, such that this is 0, then yes, that can be 0. So there's so many possibilities for this. One possible condition is, this is condition, by the way. One possible condition could be, hey, this can happen if y is equal to 1, right? If y was equal to 1, and you can have a number of possible solutions here. Minus 2 plus 2x is equal to 38. So I take this as 36. 5 is equal to 36. So add the location at 36 divided by 5, and that's going to give you approximately 30. This is 7.20. Okay, or 7.2. So at this location, at the location 7.2 comma 1, x and y, you can say your flow can be modeled as compressible flow. Okay, so this is another application of how we do these problems. And if I asked you a simple question, is this flow rotational or it's not rotational? Is the flow rotational or irrotational? How do we know that? Well, we knew that if my vorticity was different from 0, then it was rotational, because it had a value. That means it is rotating. If my vorticity was equal to 0, then it was irrotational. Okay, so when you look at the problem now, you know that vorticity is equal to this value right here. So what you're saying is that omega is equal to 13K. It is not equal to 0. So therefore, your fluid is rotational. Okay. Now, for the fluid to be irrotational, we will have to have this equal to 0, which actually it consists in taking this term right here, okay, and setting that completely equal to 0. So this has to be 0. The only possible way that can happen if you have any combinations of x and y such that they meet this criteria. Okay, any combinations of x and y that meet this criteria. In other words, let's for an example, if y is equal to 1, if y was equal to 1, then in this case x would have to be 1/3. If that location, the fluid is irrotational. If y was equal to let's say 2, let's say 3, your x will equal to 3, right? Because this is 9 and then it becomes 3. If y was equal to 2, then this is 4, x would be 1.33. So these are all the possible combinations where this fluid is actually irrotational. So what you could do is you could now plot this with many values. You could just go ahead and plot this equation right here and find where this is actually irrotational. So this is equal to 0.333, and if this was 0, then you have x equal to 0. So if I'm going to plot this, now let's do a plot putting x here and y here. So if I put this 0, this is 0. If I put y equal to 1, this is 0.33. So let's put 1, 2, 3, 1, 2, 3. So if I put 1, my point is right here. If I put value of 2 is 1.33, value of 2 is about here, 1.33. If I put the value of 3, I get a value of 3. So what you can see is that your fluid, the rotational path of your fluid for this particular fluid particle is actually looking something like this. Okay, where these are your location of the points where this is intersecting. So now if I have a fluid particle, you can say, hey, it is rotational along this path. Everywhere else it will be rotational. So this is the irrotational path. Okay. So this concludes example number 1, kind of understanding how all these equations actually work together and how we can really understand them.